So, we saw what the aim of number theory is, it is solving Diophantine equations, and we saw why we need to consider extensions of rational numbers even though we are seeking solutions only in rational numbers or integers. So, the main aim of this course, which is the main aim of algebraic number theory, is to solve is to study extensions of rational numbers. So, these are finite field extensions of rational numbers, these are called number fields. So, I am going to assume familiarity with field theory, Galois theory and abstract algebra in this course, but I will still recall a few notions here just to because it will help me set up the notation. So, the first section is number fields. Okay. So, before that let me recall what the definition of a field is. So, a field is a triple f with addition and multiplication such that f with addition is an abelian group and its additive identity will be denoted by 0 as usual, okay. And f minus the additive identity with multiplication is an abelian group again, okay, plus it satisfies distribution. So, multiplication distributes over addition. So, if I take a plus b times c, this is same as c times a plus b, which is same as a times c plus b times c, or c times a plus c times b. Okay. So, a field will usually be denoted by just f, we will not write the plus and the dot with it. So, we will just say that f is a field. Okay. Now, if f is a field, then extension of f, or field extension to be precise, is another field, is a field K containing f as a subfield. Okay. So, that is what a field extension is, and we will denote it usually by K over f. So, notation K over f is a field extension. Okay. So, if K over f is a field extension, then K is a vector space over f. Okay. So, I will also assume some familiarity with linear algebra because we will need this. So, any field containing another field, the bigger field is a vector space over the smaller field. Okay. So, we say that K over f is a finite extension or finite field extension. So, I will drop the word field from now on because it is clear that it will always be field extension, is a finite extension if K is a finite dimensional vector space over F. Okay. Otherwise, it is an infinite extension. Otherwise, K over F is an infinite extension. Okay. And degree of K over F, which is denoted as K F, this is equal to dimension okay, yeah, this is equal to dimension of K as F vector space. Okay. So, this is in general it can be infinite, but we will be mostly interested in finite extensions. So, let me look at some examples. Okay. So, F over F is a field extension, it is always a field extension like this, right, of degree 1, and this is the only field extension of degree 1. Okay. For any field F, F is the only field extension of F which has degree 1. All right. Next example that we will look at is complex numbers over real numbers. This is a field extension of degree 2. Okay. Or you can think of R as a field extension of Q, real numbers or even complex numbers as field extension of Q is an extension of infinite degree. Okay. So, our main aim is to study finite extensions of number of rational numbers. Okay. So, a number field is a finite field extension of Q. Okay. So, that is what a number field is, and these are our main objects of study and objects contained inside number fields. Okay. All right. So, recall the definition of what an algebraic number is. Okay. So, let L over K be a field extension we say that alpha in L is algebraic over K if there exists a non-zero polynomial f of x in k x such that f of alpha equals 0. Okay. So, when do we say that alpha is algebraic over k? If it is a root of a non-zero polynomial f of x with coefficients in k. All right. Otherwise, we say that alpha is transcendental over K. Okay. So, you may have seen this definition only in the context of rational numbers, but this definition makes sense for any field extension, and that is what I am giving you here. So, here is a small lemma. If L over K is a finite extension, then every element of L is algebraic over K. It is an easy statement to prove, and you may have seen the proof of this before. So, let alpha be an element of L and assume that alpha is not equal to 0 or 1, because both 0 and 1 are contained in K, and so they will be algebraic over K. So, let us say that they are different from 0 and 1. So, you consider the infinite set . 1 alpha, well, okay, maybe okay, maybe let me not say infinite set here, because it may not be infinite. Let me just say consider the set alpha cubed, etc. Okay. So, if alpha to the n is not equal to 1 for all n bigger than or equal to 1, then this set is infinite. Okay. So, what happens if alpha to the n is equal to 1? So, if alpha to the n equals 1 for some n bigger than or equal to 1, then alpha is a root of f of x equal to x to the n minus 1, which is obviously in k x for any field k. So, we assume that this is not the case. Alpha to the n is not equal to 1 for all n bigger than or equal to 1, then 1 alpha, alpha squared, etc. is an infinite set, but L over K is finite dimensional. Right. Hence, this infinite set is linearly dependent. Is linearly dependent over K, which means that there exist A0, A1 up to some Am in K, not all 0, such that A0 plus A1 alpha plus A2 alpha squared up to Am alpha to the m is 0. That is what it means to be linearly dependent. Okay. Then alpha is a root of this polynomial f of x, which is summation I going from 0 to m a I x to the I, and this is a non-zero polynomial in k x. Okay. So, that proves the lemma. So, in particular this means that, so in particular all elements in a number field. Remember, we defined number field as a finite extension of Q. So, all elements in a number field are algebraic over Q. These are also called algebraic numbers. Just sometimes we just call them algebraic numbers when we do not want to say over Q. Okay. So, this allows us to do the following thing. So, what we do technically is we fix an algebraic closure Q bar of Q. Okay. So, you may have seen in Galois theory or field theory that any field has an algebraic closure. Algebraic closures are, if you take two different algebraic closures, they are isomorphic, but the isomorphism is not unique, and that is why it's, you have to fix a choice of algebraic closure and work with that. So, we will fix an algebraic closure Q bar of Q. So, these are all algebraic numbers over Q. So, if you want to work more concretely, you can work with complex numbers and then take all algebraic numbers inside the set of complex numbers, and that will be one of the avatars of Q bar. So, you can fix it in any way that you want. We are not going to say that everything is contained in C, but I am going to fix an algebraic closure Q bar of Q and then work with this. Okay. So, every number field will be subset of this Q bar. Okay. So, that is just a technical point that we will always fix an algebraic closure and work with that. All right, and we can do that now because number field consists of algebraic numbers. So, they are all contained in Q bar. Okay. All right. So, this is our number field. Now, we want to study what are called rings of integers in a number field. Okay. So, this is our second section, rings of integers in number fields. Okay. So, algebraic numbers are numbers that are algebraic over Q, but one can define a notion of what it means to be algebraic over Z, the set of integers, and that is what I am going to do next. And then we will consider all elements that are algebraic over Z. These are called algebraic integers. So, let me define it first. So, let K be a number field okay. We say that alpha in K is an algebraic integer if there exists a monic polynomial. So, the leading coefficient is 1, monic polynomial f of x in zx. So, no longer just in qx, but even in zx, such that f of alpha is 0. Okay. So, it has to be a root of a monic polynomial with coefficient in z. So, let us see examples again. So, if you take alpha to be square root of 2, then this is an algebraic integer, because you can take f of x to be x square minus 2. So, square root of 2 is an algebraic integer. But here is an example slash exercise. If you take alpha to be half, this is not an algebraic integer. Okay, and so on and so forth. So, you roughly speaking, you should think of algebraic integers as not having denominators, and things that have denominators are not algebraic integers. So, just like integers, and this will become precise as we move on, as we study other things in the course. Okay. So, let us prove a proposition that gives you various equivalent ways of thinking about algebraic integers. So, let k be a number field and alpha be an element of k. So, I can, for this I can always talk about just q bar, let alpha be in q bar, but anyway let us do the following. Then the following are equivalent, the following. So, usually I will use the shortcut like this, but since this is the first time, let me write it out. The following are equivalent. This means the following statements are equivalent. Okay, so, this is a standard abbreviation that is often used. So, if I take the smallest ring containing z and alpha, this is denoted by z alpha, right. So, this consists of all polynomials in zx evaluated at alpha, that is one way of thinking about it, is a finitely generated z module. Okay. So, that is my first statement. This statement is equivalent to alpha is an algebraic integer. This statement in turn is equivalent to saying that the monic minimal polynomial of alpha over rational numbers is actually contained in zx. So, it has coefficients in z. Okay. So, you take the monic minimal polynomial. So, again from field theory you should know that such a polynomial always exists, a minimal polynomial of an algebraic element always exists, and if you take the monic one, then the third statement says that this is actually contained in zx. So, we want to prove that these statements are equivalent. So, let me quickly, again this is something that you may have seen in a course on field theory or in a course in algebra. So, let me quickly try to prove this for you. So, I want to prove that 1 implies 2. So, what does the statement 1 say? It says that z alpha is a finitely generated z module. Okay. So, it means that z alpha is generated as a z module by finitely many elements. So, let f1 x up to fr of x in zx be such that f1 alpha, f2 alpha and all these things up to fr alpha, these are elements in z alpha generated z alpha over z. Okay. So, that is precisely what 1 gives me, finitely many polynomials such that when I evaluate them at alpha, these give me elements of z alpha and they generate z alpha as a z module. Okay. Now, you take n to be bigger than max 1 less than I less than equal to r, degree of fi of x. So, these are all polynomials. So, they have some degree, it is an integer. I take all those finitely many numbers and I take an integer n bigger than all of those. Okay. So, maybe not just equal to, but bigger than all, strictly bigger than all of them. Okay. And I consider alpha to the n, which is also an element of z alpha, right. And because z alpha is generated by f1 alpha, f2 alpha, etc., there exist a1, a2, ar in z such that alpha to the n is equal to a1 f1 alpha plus a2 f2 alpha, so on up to ar fr alpha. Okay. So, now I take f of x to be x to the n minus summation I going from 1 to r ai fi of x. Okay. So, because my n is bigger than degree of any of these fi's, this x to the n is not cancelled by any term in this second part. Okay. So, this is in zx, and f of x is a monic polynomial. Okay. Furthermore, just by this relation star, f of alpha equals 0. Right. So, this means that alpha is an algebraic integer. So, that is 2. So, we have proved 1 implies 2. Okay. Next, we consider two implies 3. So, let me take you back to what 2 is. 2 is that alpha is an algebraic integer, and you want to show that the monic polynomial of alpha over q itself is a polynomial with coefficients in z, right. Being an algebraic integer means that it is a root of a monic polynomial with coefficients in z, but that need not be the minimal polynomial a priori, right. A priori it could be of a bigger degree, but this statement says that actually, I mean 3 says that that does not happen, right. 2 implies 3 says that that does not happen. So, let f of x in qx be a monic polynomial, be the minimal polynomial, sorry, be the monic minimal polynomial of alpha over q, and 2 tells me, so as alpha is algebraic integer, there exists h of x in zx monic such that h of alpha is 0. Okay. But by definition or by an easy lemma, depending on how you define minimal polynomial, we know that f of x divides h of x in qx. So, this division does not happen in zx because f of x need not even be in zx. So, there exists g of x in qx such that f of x times g of x equals h of x. Right. And what is our aim? Recall that our aim is to show that f of x itself is in zx. Okay, that is what we want to show. So, let d1 and d2 be smallest integers, smallest positive integers such that d1 f of x and d2 g of x are both inside z of x. So, I am just clearing the denominators, I am looking at denominators of all coefficients of f of x and taking their LCM, that is what my d1 is. I am taking denominators of all coefficients of g and taking their LCM, and that is what d2 is, and my aim is to show that d1 is 1. Okay. So, that is what we want to show. Right. So, what we have now is d1 f of x times d2 f g of x is equal to d1 d2 times h of x. Okay. So, if p is a prime number dividing d1 times d2, then d1 d2 h of x is congruent to 0 mod p, right. Coefficient of h are already integers and p divides d1 d2. So, all the coefficients of d1 d2 times h of x are divisible by p. So, we have this congruence. On the other hand, d1 f of x is not congruent to 0 mod p and d2 g of x is also not congruent to 0 mod p. Why? Because if all coefficients of d1 f of x are divisible by p, then we can divide out by those coefficients and my d1 can be replaced by d1 over p, or my d2 can be replaced by d2 over p. Okay. So, one of those can be definitely replaced by the quotient d1 over p or d2 over p, and that will contradict the fact that d1 and d2 are smallest such choices. Okay. And so, we get okay, but yeah, so we get d1 f of x times d2 g of x, right, mod p, you have a field. So, this is there are no 0 divisors, right, but that is a contradiction. Because d1 f of x d2 g of x is equal to d1 d2 h of x, which is congruent to 0 mod p. Okay. So, hence there does not exist any prime dividing d1 d2, and if you have a positive integer that is not divisible by any prime number, this means that that positive number itself is 1, and so hence d1 is equal to 1 and f of x is in zx. Okay. So, that is 3, that is what we wanted to prove, right. So, we have proved 2 equal to 3. So, let me finish this lecture by proving 3 implies 1. So, what is 3? Let me take you back to the statements. So, 3 says that the monic polynomial of alpha over q is contained in zx, and from that I want to prove that z alpha is a finitely generated z module. Okay. So, let f of x equals x to the n plus a n minus 1 x to the n minus 1 and so on up to a1 x plus a0 be in zx such that f of alpha equals 0. So, that is my polynomial given by 3. Then alpha to the n is minus a n minus 1 alpha to the n minus 1 minus a n minus 2 alpha to the n minus 2 and so on, minus a 1 alpha minus a 0. Okay. So, in particular alpha to the n is in the z module generated by 1 alpha up to alpha to the n minus 1. Once you have that, you can write alpha to the m as alpha to the m minus n times alpha to the n. So, for m bigger than or equal to n, we can always do that and proceed inductively. Okay. So, I will leave the rest of this as an exercise, but that proves that z alpha is finitely generated over z. Okay. So, I was told to do it in half an hour, 35-minute slots.
Yes, sir.
Yeah, okay. So, maybe I will take a 2-minute break and
You have to complete this.
what do I have to do?
Like we'll see in the next class. Summary.
Okay, summary, sorry, yeah. So, in the next class, we will look at more properties of the ring of algebraic integers. Okay. So, right now we have proven we have proven properties about algebraic integers themselves. In the next class, we will prove that the set of all algebraic integers in a given number field forms a ring, and once we have that ring, we will start studying its properties.